Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 9th, 2025, about 4 days ago. It pinpoints when multi-agent systems actually beat a single language model agent, and it backs this up with a predictive scaling model that reaches cross-validated R-squared of 0.513 and even 0.89 when generalizing to new task domains. The paper is titled, Towards a Science of Scaling Agent Systems. And as we will see later, the results offer concrete rules of thumb for deciding when more agents help and when they just get in the way. Alright, the previous segment laid out the big question, and Figure 1 now shows how performance scales across model intelligence and different agent setups. Each panel compares single agent baselines to several multi-agent variants, plotted against an intelligence index. The three panels cover OpenAI GPT models, Google Gemini models, and Anthropic Claude models, so the pattern is robust across vendors. Centralized and hybrid teams usually climb above the single agent lines, while independent agents sometimes lag, especially at higher intelligence levels. Well, Figure 1 showed how coordination interacts with model intelligence, and Table 1 now clarifies what kinds of tasks drive those results. The table lists 4 benchmarks: Browse Comp Plus for multi-website information search, Finance Agent for entry-level financial analysis, PlanCraft for Minecraft-style environment planning, and Workbench for everyday business workflows. Each benchmark specifies a distinct task family and an evaluation design, so together they span web browsing, finance, open-world planning, and office-style tool use. So, while Table 1 mapped out the task space, Table 2 spells out the computational trade-offs of each agent architecture. The table compares single-agent systems to 4 multi-agent designs on large language model call counts, sequential depth, communication overhead, and memory. Single agents have 0 communication cost, but no parallelism. Independent teams gain n-way parallelization with modest overhead, whereas decentralized and centralized teams incur extra rounds of debate or orchestration, and hybrid teams pay the highest coordination price. Alright, Table 2 detailed the raw costs of coordination, and Figure 2 shows what those costs buy in terms of accuracy. The top left panel, Browse Comp Plus, shows that independent teams actually hurt performance, while more organized teams barely beat a single agent. The top right Finance Agent panel shows big gains for all multi-agent setups, which thrive on parallel financial subtasks. The lower left PlanCraft panel shows severe degradation from any team, whereas the lower right Workbench panel stays roughly flat, with only small positive or negative shifts. Well, Table 4 spells out which factors actually drive performance in the scaling model. The main effects show that raw intelligence has a mixed role, with a small negative linear term but a positive intelligence squared term, meaning higher capability yields accelerating returns. Tool diversity, captured by log of 1 plus tool count, strongly helps, and the single agent baseline acts as a proxy for task difficulty. Critical interaction terms then reveal the key trade-offs, including the efficiency tools trade-off, and strong penalties when overhead or error amplification meet many tools. So, while Table 4 highlighted which variables matter in the model, Table 5 shows the raw coordination metrics for each architecture. The table reports success rate, turns, overhead, and efficiency, all normalized so that single agents set the baseline. Multi-agent setups need far more turns and incur huge overhead, especially hybrid teams, which reach over 500%. Error amplification explodes for independent agents at about 17 times single-agent levels, which explains why loosely coordinated teams are so brittle despite similar average success rates. So stepping back, 2 lessons stand out. More agents are not always better because coordination overhead and error amplification can easily wipe out gains. And the right architecture depends on task structure and model strength, not just raw scale. This kind of predictive science makes agent design less guesswork. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.